I want to talk about evaporation now, and I think there are some surprises in store. The general idea about evaporation is somewhere between we don't know how it works, as one atmospheric scientist said to me, we don't really understand it. And the idea that water gets a kick of kinetic energy and the water near the surface, the molecules evaporate. And I'm going to suggest that's not entirely true. All you need to do is to go to Starbucks to prove the point. You take a cup of water, a cup of coffee or tea or whatever is your preferred drink. And if it's dark at Starbucks and you could find a wall that's a dark curtain, and you look at the evaporating water, this is what you see. You take a photograph. Now, if you think about it, it's peculiar in several different ways. The first way that it's peculiar is you'll see that there's a kind of a puff here and a puff here. It's not continuous. And you can see this at your own home or wherever you want. Just take some warm water, or hot water is even better, with lighting and a dark background, and you can then see that. So what does that mean? When my son, who's the artist who illustrates my book, took a picture, we had a lot of discussion about this. The first thing is that you see the vapor. Now, the vapor is obviously evaporating water, and if you can see the vapor, what does it mean? In order to see something, it needs to be big enough. The reason you don't see the air is that the molecules of air are so small, they don't scatter a whole lot of light, and therefore you don't see the air. But if the air molecules were huge, then you could actually see the air molecules. And so the fact that you're able to see something, anything at all here, means that what's coming up is large enough to scatter light. Now, large enough, what does that mean? Well, the wavelength of light is about half a micron or 1 micron, 1 micrometer. And so the scattering entities, whatever's coming up here, has to be in clusters of at least 1 or 2 or 3 micrometers. It turns out they're actually 30 or 40 micrometers in order to be seen. Now, how many water molecules is that? It's not 1 or 2 or 5 or 10. It's gazillions of water molecules. A huge number, too large to count. Well, not too large to count, but extreme. I forgot the number, but it's billions or trillions or something like this, not 1 or 2. I believe that you can take that as a fact, shall we say. It's well established in physics, and I don't think there's any argument against it. It's just you can see big things and you can't see small things. It's as simple as that. And so this is evaporating water, and you can and the next slides are going to tell you more about the character of all this, how it happens and what's going on. But as far as I know, this is unknown among the people who study clouds and such. One of the students in the lab decided to take a cross-sectional view across one of these. So what do you expect? Through one of these. In other words, cut through and see what you see when you cut through. I don't know if he was as surprised as I was when he showed it to me, but these are representative samples, A, B, C, and D. And they came as a shock to me. I hope they come as a shock to you, unless you've seen this before. And so all of the scattering is occurring in these white areas. The dark areas don't scatter anything. You don't see it. There's nothing there. This is a slice through. And so it looks like it's got various contiguous units together with one another, kind of like a pretzel, with nothing in between here, everything occurring at the edges. And remember, this is all rising up. This is a slice through what's rising up. So we thought, if this is rising up from the cup of water, we thought, what's in the water? Maybe you find the same structure in the water, and it's just whatever structure was in the water is simply rising up. What's in warm water? I don't know how well you can see this. It barely shows, but I can see it on the slide. I can see these white lines here, very similar to what is rising up, which means whatever you see in the cloud actually originates in the water. And here's a better view of the warm water. It's a better view because not only because it has the quality of art that I could almost put on one of the walls of my home. It's really lovely. And this is just warm water in a pan, and it's illuminated not from directly up above, but from an angle, a very low angle, almost horizontal. And what it shows is dark and white regions. It definitely shows this cellular shape inside the water more clearly than here, but it's really the same. It's essentially the same. You've got dark regions and light regions. The reason that you see this is that the lighter regions are higher than the darker regions. And so the darker regions are like valleys, and they don't get illuminated because the light being at a very low angle never reaches them, so they appear dark. So these are valleys and these are hills. Something from beneath is pushing up to create those hills, okay, but not here. And I mean, those are some hints, but the important point is the water contains structure to it. Now, another way of looking at it where you can see this structure a lot better is using an infrared camera. And the infrared camera gives you an image based on how much it is being emitted in terms of infrared wavelengths. And you can see that the dark regions here, that there's not much infrared being emitted. Someone might have a tendency to think of them as cold, but it means essentially that there's not much infrared coming, but there's lots of infrared coming from in between, from the island in between. And we would reflexively interpret this as cool and hot, but in actuality, it's the amount of infrared energy that is being detected. So what does that mean? And then I go back a couple of years to experiments that we did on water, where we looked at a substance called naphion, which nucleates, sitting next to water, which nucleates a very nice exclusion zone. And we looked at the infrared energy coming from the naphion, the EZ, and the ordinary water. And what you notice here is that the EZ region, which is right adjacent to the naphion, is dark. It means the EZ is not emitting very much infrared energy because we're measuring infrared energy. Dark means nothing's coming. A dark region, we learned, could correspond to the EZ region. And whereas the ordinary liquid water region shows a lot more scattering, a lot more emission. So dark means radiates less than bulk water. Could this be EZ that we have here because it's dark, similarly dark? Well, how do these rings form? And we could look at them, the incipient rings during their formation, and you can see there are little dots. So they form from, we're not sure, from either droplets or bubbles, but some round-like entity. And we were able to deduce through a lot of studies, again, it's in the book, but I don't have time to summarize, that either a droplet or a bubble looks like this, droplet looks like this, and we were able to determine that there are EZ shells in both cases, filled with positive charges in between. In one case, vapor, the other case, liquid. But the positive is pushing out against this membrane of negative, and that's the reason why droplets and bubbles are spherical. So we call them, the two of them, water vesicles because we can't always distinguish between droplets and bubbles. They kind of look pretty much the same. And when we've done experiments and we thought we'd have a bubble, it turned out to be a droplet and vice versa. So we're not sure. And so we decided to assign a collective name to all of them. We call them vesicles. It could be a droplet, could be a bubble, but the important point is they have net negative charge. This is a critical point. And why do they have a net negative charge? Because as they're forming, the layers of EZ grow and the positivity grows, and some of that positivity escapes before this is able to enclose a sphere. So since some of the positives have escaped, you have fewer positives than negatives, and therefore this has a net negative charge. And that's important. Obviously, there's a lot more evidence that I don't have time to present to you. So we then wind up with a hypothesis that these lines may be vesicle clusters. Again, we don't know droplets or bubbles. We can't make that judgment, but it looks like a line of these consists of a whole lot of these stuck together. And if you're still with me, you're thinking, well, this is impossible, right? Because each one of these has negative charge. And we learned in middle school that negative charges repel each other, and therefore this should be repelling this, and it should never get together and aggregate to form this kind of boundary. However, is a possibility that these negative charges or negative entities are actually glued together by protons sitting in between them. And I'll go back to a general principle of this. And the general principle comes from none other than the great physicist Richard Feynman. In his lectures, he discusses this, and it's a phenomenon which he calls like likes like. What does that mean? It means that if you have two bodies that have like charge, let's say the two bodies have negative charge, they like each other, and therefore, because they like each other, they come together. His pronouncement, not mine. This is the great Nobel physicist who many consider the Einstein of the second half of the 20th century. He said, like likes like because of an intermediate of unlike. He's famous for that. And I think it was even in his Nobel lecture. And so the idea is that if you have in the positive in between negatives will begin to come together. So he says, quote unquote, like likes like because of an intermediate of unlikes. And it shows up in The Tale of Genji, the first novel, where you have warring parties and the parties will never, ever get together unless you put the appropriate attractor in between. So that's 1,000 years ago. The ancient Japanese knew about like, likes, like because of intermediate of unlike. So our going hypothesis is that these lines are actually negatively charged clusters held together, glued together by protons. You just need a few protons in between to hold it, essentially hold it all together. So please bear that in mind. These are negatively charged entities. We found that by imaging using an infrared camera that it's not only a surface phenomenon, but that these lines actually extend down. So these dark lines, whether they're accounted for by this structure or not, or whatever, it's not just surface, but it extends down. And so the mosaic cells are actually mosaic tubes. And so back to the mechanism of evaporation, partial mechanism of evaporation, I should say. I'll tell you why in a moment. What we found is if we take a cross-section through this, it looks something like this. And in fact, as this is rising up, we can do subsequent cross-sections. They all look pretty much the same until this is all evaporated. And then the pattern changes completely, starts all over again. Another set of these columns begins forming and then rises up. So evaporation, at least in part, I'm not saying all of evaporation, occurs in this manner. And that's why, that's what you see in the coffee rising from the coffee cup. Each one of these blobs corresponds to some of these structures having formed, having risen, and then new structures form again, and it will start to rise. So each one of these clusters is one of those formations that occurs. That's what we were able to deduce. Now, why am I saying or hinting this is not all of evaporation? Of course, not many or very few people know about this phenomenon other than those who have read our papers or read our books, but it can't be all of evaporation. And why can't it be all of evaporation? Well, because these are negative charges, these blobs, these clusters, you see. And if negative charges keep rising from the Earth will progressively become more positive. And you can imagine that over a period of a half day or so, but not over a period of 1 billion years. The Earth can't continue to become positive. So there must be some positive charges that are either emerging evaporatively from the Earth. And I'd like to suggest to you, I should have put the slide in there, that it has to do with this because remember, I said these areas are bulging upward. Why are they bulging upward? That's the only reason you can see them, because light is coming in at an angle. They're bulging upward because these are full of protons for reasons where I don't have time to discuss, but you could certainly, it's in the book, and the protons are pushing up on the surface. The protons are in fact hydronium ions, right? Because the positive charges will stick to water molecules. So the protons become hydronium ions, and the hydronium ions are pushing up. And they will also, as they're pushing up, there's a pressure that's pushing up on these surfaces, and they will come through and rise up. And so you have two components of evaporation then, the one that I've shown you so extensively over here, and also protons coming out. So now if you consider these droplets essentially rising upward in humid weather, you'd expect something like this. You'd expect the protons to be there. You'd expect also these blobs that I've shown you, negatively charged blobs. And if they're sticking together, say, for example, in clouds, and you get clear regions, or you get these regions devoid of these light scattering blobs, then it appears clear. And so if you have humid air if you have a building or something far in the distance, it doesn't appear very clear because the light gets scattered multiply by all of these blobs, which are large enough to scatter light. Obviously, otherwise you wouldn't have seen them in Starbucks. If you have the clouds, and the clouds have sopped up pretty much all of these vesicles, then it becomes clear, and then there's no problem seeing distant buildings. So this is Washington, D.C. in August, and this is perhaps Minneapolis in nice, brisk winter weather. So evaporation, just to summarize, is different from our evidence, is that it's different from what people have surmised.